Okay guys, here we go again. Another video. So we're going to, on this video, learn how to take limits of these summations. So just to start out with, we are going to pretend that this graph is y equals x squared, even though it's not. So just bear with me on that one. So real quick, the area of this curve here, using right rectangles, is right here. It's 1/3. Because each rectangle is 1/3 long. And remember, we get 1/3 by taking b minus a, or 2 minus 0, and divide it by how many divisions we want, which are 6. So that would turn out to be 1/3. Then we come over here and we have to figure out the first height of the rectangle. So we stick 1/3 into the function and get a y value, which would be the height of the first rectangle. Then we come over and take 2/3. Plug it into the function to figure out the height of the second rectangle, and so on. So hopefully this right here makes sense to you. But now what we want to do is make these rectangles smaller and smaller and smaller, because the smaller we make them, or in other words, the more of them we make, the better our area will be. So let's see, what are we going to do here? We are going to make a lot of rectangles and then take a limit as n approaches infinity. Alright, so what I'm going to do first is redo the first problem that we just did, only I'm going to try and make it a little bit more expanded so that you can see exactly how it gets turned into a summation. So right here is what I had earlier written just a little bit differently. We have the base of each rectangle, which is 1/3, and then we're going to plug into our function 1 times 1/3. And I write it that way because I am going over one distance of 1/3 to get the height of the first rectangle. The height of the second rectangle is when I stick 2 units of 1/3 into my function. So if you go down here, the second rectangle's height is 1, 2, 1/3 units. And that's what this is supposed to represent here. The third rectangle, we're going to go over 3 1/3 units. So on the graph, 1, 2, 3 1/3 to get the height of the third rectangle. And then I finished off with the last 3 rectangles. Well, I wrote it this way so that you can see that every single height has a 1/3 value that gets stuck into the function. And then I have a sequence, 1, 2, 3, 4, 5, 6. So what I can do is write that in summation notation now. So my area is 1/3 for the base. I just pulled it out front because it's a constant. And then I'm going to sum from 1 to 6. My function evaluated at I times 1/3. And I is going to represent that 1, 2, 3, 4, 5, and 6. Then I can simplify this more. I still have the 1/3 in the summation, but now what I do is I'm going to actually stick I over 3 into y equals x squared. So I'm going to take this right here, and I'm going to plug it into my function, which is y equals x squared. So this thing there gets put in for x, and I get I over 3 squared. That's the hardest part, I think, to understand. So hopefully that's fairly clear. If not, let me know. Send me a note. Then what I'm going to do is do a little bit of simplifying. So I'm going to go ahead and square that, which is where I get to here. And then that 1/9 can come out front because it's a constant. And I'm just left with I squared inside. And now according to those definitions, we know what the summation of I squared is. And it's right here. N times n plus 1 times 2n plus 1 over 6. And then I would stick 6 into there to figure out the area using 6 rectangles. Okay, now what we're going to do is make it even more generic. We're going to cut this region into n rectangles, not 6. So our new base for each rectangle is not going to be 1/3 anymore, but it's going to be 2 minus 0 divided by n, and n is an unknown value right now. So here's what the heights of our rectangle are going to be. Instead of f of 1 times 1/3, and then 2 times 1/3, and then 3 times 1/3, it's going to be 1 times 2 over n, and then 2 times 2 over n. And then we're going to go over 3 units that are 2 over n long. So in case that's confusing, because it usually is, pretend these numbers up here now are going to be 2 over n, and then this would be 2 over n's, and this would be 3 2 over n's, and 4 2 over n's, and 5 2 over n's, so that we can write it this way so it's easy to put into a summation formula. Now that's the hard part. Once we get past this right here, I think we got it. So I'm just going to go through here and write down every step that I did prior using the n. So here's our area. Our base is 2 over n. We're going to sum now, not from 1 to 6, but from 1 to n, however many rectangles we are doing at the time. And so then, as you saw up here, it's 1 times 2 over n, 2 times 2 over n, 3 times 2 over n, and so that's where this came from. I'm putting 2 over n times 1 and then 2 and then 3 into my function. And remember, it's y equals x squared again. So then we come here and we pull the 2 over n out. It's still out. Now I'm just going to plug into the equation. So I actually took this 2i over n and squared it, because that's what my function tells me to do. And then I'm going to simplify it. So I get 2 squared, which is 4, over n squared, I squared. So that's just simplifying this right here. The next step is to pull out 4 over n squared. And remember, n is a number of rectangles that we want to make. So it's a constant. So it gets pulled out front. The only constant variable we have here is the I. The I is the index that's changing. So that can't be pulled out. Once we get to this point, we still have this on the outside, but our summation formula for I squared I have written here again. And then I'm going to multiply everything out. And then I'm going to simplify, so I'm going to multiply through, and then actually what I did was I took 2 into 6 3 times, and then I multiplied the 4 through this top. And now to find now at this point in the process, I can do 10 rectangles, I can do 20 rectangles, I could do 50 rectangles, and I would just stick the number of rectangles into this formula. But to get an exact area, I want to take a limit as n approaches infinity. In other words, I want an infinite number of rectangles. So that's what we're going to do. The best way to do this is to break each fraction, to break that up into 3 individual fractions. And then we need to simplify each fraction. And now, as n gets large, the second 2 fractions, this one here and this one here, those will approach 0. So the limit is going to be 8/3, which turns out to be the exact area under our curve between 0 and 2. I hope this helps. Please hear this though. On your homework, only do right rectangles. The left rectangles are a little harder. The midpoint rectangles are harder yet. So if you will just work those problems in the 50s there,